Hello, my name is Sergiy Butenko. I am a professor of industrial and systems engineering at Texas A&M University, and the title of my presentation is an improved approximation for the maximum k-dependent set on bipartite graphs. This is a joint work with Hosseinian, who is our recent graduate and is currently a postdoc at Rice University. So here is the content of my presentation. I will start with an introduction, then I will discuss the algorithm and its analysis. In fact, we'll prove the approximation ratio, and then I will conclude with some remarks. Let's start with the definition of a k-dependent set. Given a simple undirected graph G with the set of vertices V and the set of edges E, and the positive integer constant k, a subset S of vertices is called a k-dependent set if the degree of every vertex in the subgraph induced by S is at most k. For example, if we look at this graph right here and the subset of vertices 1 and 3, then this set will form a k-dependent set for k equal to 1. In fact, we can show that this is a maximal one-dependent set, meaning that it is not a subset of any larger one-dependent set, but it is not the largest one-dependent set in the graph, because if we look at another one consisting of the remaining vertices 2, 4, and 5, then we can see that corresponding induced subgraph contains 3 vertices, and it is a one-dependent set, and it happens to be the maximum one-dependent set in this particular graph. In this talk, we are interested in the maximum k-dependent set problem, which is to find a maximum cardinality k-dependent set in a given graph G. This problem is closely related to some classical optimization problems in graphs. In particular, if we allowed the value of k equal to 0 in the definition of k-dependent set, then zero-dependent set problem would be exactly the maximum independent set problem, which is to find the largest subset of pairwise non-adjacent vertices in the graph. The problem is also equivalent to the maximum S-plex problem in the complement graph G bar of G. So this is exactly the k-dependent set problem if we set S to the value of k plus 1. Now, what do we know about the complexity of this problem? For any k greater than or equal to 0, the maximum k-dependent set problem is known to be NP-hard. Moreover, it cannot be approximated within the factor of n to the power 1 minus epsilon for every epsilon greater than 0. There are a few known polynomial time solvable cases, which include cographs, split graphs, and graphs with bounded tree width. On the other hand, it is known that the problem remains NP-hard on unit disk graphs and planar graphs. However, we have a constant ratio approximation and a polynomial time approximation scheme for unit disk graphs, and we also know that there exists a polynomial time approximation scheme for planar graphs. In this work, we are interested in approximability of yet another hard case, which is the case of bipartite graphs. For this case, we have an approximation algorithm with the ratio of 1 plus k over k plus 1, which was proposed by Kumar and his co-authors for a more general problem known as the maximum pi k1 k2 subgraph. So this is a problem considered in bipartite graphs, where we are looking for the largest subset of vertices with no more than k1 vertices coming from one part and no more than k2 vertices coming from the other part. And the subset of vertices is supposed to satisfy a certain property pi k1 k2 in the induced subgraphs. The approximation algorithm they proposed for this problem is based on the iterative rounding applied to a sequence of optimal solutions of the linear programming relaxations of the integer programming formulation. And when it is applied to our particular case of this problem, the maximum k-dependent set problem, it provides a 1 plus k divided by k plus 1 approximation algorithm. This is the only known approximation algorithm for the considered problem to the best of our knowledge. And again, we are looking at the k-dependent set problem restricted to bipartite graphs. So here is the formal statement of our problem of interest, the maximum k-dependent set in bipartite graphs, abbreviated as written here. So we are given a bipartite graph G with the set of vertices V and the set of edges E and an integer k greater than or equal to 0. And we want to find a maximum cardinality k-dependent set in G. The main contribution of this work is a simple combinatorial algorithm with the approximation ratio given by 1 plus k divided by k plus 2, which is a slight improvement over 1 plus k divided by k plus 1 approximation ratio that we mentioned earlier. Obviously, the improvement doesn't look huge, but for example, for k equal to 1, we go from 3/2 to 4/3, and the main advantage of our algorithm is its simplicity to the extent that we'll be able to prove the approximation ratio during the short presentation we have here. First, let me mention a couple of definitions and the theorem that everybody probably knows anyway. So a subset of edges is called a matching if no two edges in this subset have a common incident vertex, and then a subset of vertices is a vertex cover if every edge in E has at least one of its end vertices in this subset. And the Koenig-Egervary matching theorem states that the maximum cardinality of a matching in a bipartite graph G is equal to the minimum cardinality of a vertex cover. Alright, so now we are ready to state our algorithm and to prove the approximation ratio that we claim. So the algorithm is extremely simple. So we take the integer constant k and the bipartite graph G as the inputs, and then we repeat the following k times. We find a maximum cardinality matching M in the graph G, and then we remove that maximum matching from the graph, and we repeat this process k times. Then once we are done with these k steps, we find a maximum independent set that we denote by S in the residual graph G, and we return this set as the answer to our problem. Now, since S is an independent set in the residual graph, and this residual graph is obtained from the original graph after removal of k matchings, clearly when we put all these matchings back, the degree of every vertex in the induced subgraph for S will be no more than k. So clearly S is going to be a k-dependent set in the original graph. Let's look at an example for k equal to 1. So here we have this bipartite graph, and the white vertices in this graph denote the optimal solution. And let's see what solution will our algorithm find. So what we do, we just remove one matching from this graph of maximum cardinality, and this matching is denoted by dashed edges on the right figure. So we remove this matching, and this is our residual graph. And in this residual graph, by gray vertices, we denote the vertices included in a minimum vertex cover. So in order to obtain the maximum independent set in this residual graph, we can find a minimum vertex cover in this graph. And it happens to consist of 4 vertices here. So, and the remaining vertices are going to form an independent set in the residual graph. And this independent set is the output of our algorithm. And we can see that our output contains 8 vertices and the optimal solution consisted of 9 vertices. So clearly the output is not optimal, but it's pretty close to optimal. Alright, to establish the approximation ratio, we will need a few notations. We have 3 groups of notations here. The first group deals with the notations related to the algorithm. The second group are the notations referring to the optimal solution, and the third group, the interface between the optimal solution and the solution that we obtain. So in the first group, the first notation we have is mi, which is the cumulative set of edges deleted through the first I iterations. So these are the edges included in our matchings that we remove. Then gi denotes the corresponding residual graph, which is the graph obtained from G by removing mi. Finally, I with the subscript of I small is a maximum independent set of gi. So for I equal to k, we obtain the output of our algorithm, meaning that S is equal to ik. Next, we have the notations concerning the optimal solution to our problem. By ik star, we denote an arbitrary maximum k dependent set in G. So this is an optimal solution. And then dk star will be the vertices that are not in the optimal solution. So these are given by v minus ik star. And in the third group of notations, we have the notations related to both the optimal solution and our algorithm solution. So by ek prime, we denote the set of edges with both end vertices in the optimal solution ik star that are not deleted by the algorithm. So here E of G of ik star is the set of edges that have both endpoints in our optimal solution, and we remove mk from this set. And then ek2 prime will be the set of edges with both endpoints in the optimal solution that are actually deleted by the algorithm. So why are we focusing on the edges with both endpoints in the optimal solution? That's because these are the bad edges to not remove, right? So ideally we would want to remove all of those edges so that the vertices that are in the optimal solution would form an independent set in the residual graph. But unfortunately, this will not always be the case. Therefore, we'll have to focus on these edges that have both endpoints in the optimal solution ik star. Okay, our proof will be based on 3 lemmata that we'll use to establish the lower bounds on the size of this independent set that we are computing. So the first lemma states that the size of the independent set is lower bounded by n minus the cardinality of mk divided by k for every k greater than or equal to 1. For k equal to 1, the result follows directly from the Koenig-Egervary matching theorem by observing that the independent set that we find will be at least as large as the maximum independent set of G, because the residual graph contains less edges. And then for k greater than or equal to 2, we use the induction, and here is our induction assumption that the statement holds for I minus 1. And then we need to show that it holds for I as well. So for that, we represent mi as the sum of mi minus 1 plus the matching that we find in the residual graph mgi minus 1 that we have after I minus 1 steps. And we have the inequality following from the induction assumption, plus we apply the Koenig-Egervary matching theorem for representing m of gi minus 1. And finally, we use the fact that the size of the maximum independent set in the residual graph non-decreases after each next iteration because we keep removing edges. As a result, we obtain the needed inequality and the statement holds by induction. In the second lemma, we slightly weaken this lower bound on the size of the maximum independent set that we find in the residual graph. And the way we proceed, we look at the matching, the last matching that we remove, which is MK. This matching consists of the set of edges with both endpoints in the optimal solution. And recall that this subset of edges was denoted by EK2'. Then later we replace this EK2' with the difference of all the edges with both endpoints in the optimal solution IK star and the edges that were not removed that have both endpoints in the optimal solution. Obviously, this is equal to this right here, right? So, but then looking at the other edges from MK that don't belong to this set, at least one endpoint for each of these edges must belong to DK star, which is again the set of vertices that are outside of IK star. And then every vertex from DK star can have no more than K edges incident to it that were included in MK. So therefore, the upper bound on the number of edges that we remove that don't belong to EK2' is given by this product right here. So as a result, we obtain the upper bound on the cardinality of MK given by this expression right here. All right. Finally, using the previous lemma, remember we had this inequality established in the previous lemma, we just plug in the upper bound on the cardinality of MK into this inequality and take into account the fact that n minus the cardinality of DK star gives us exactly the cardinality of IK star, and we obtain the inequality that we have in the statement of this lemma. Finally, the third lemma establishes the lower bound on the ratio on the size of the solution that we obtain and the size of the optimal solution. And this lower bound is given by this expression right here. So to establish this lower bound, what we do, we consider two different cases. So IK star is either less than or equal to this ratio here or greater than this ratio here. So in case we have this ratio as the upper bound, we obtain the inequality we need very easily just by using the fact that IK star is upper bounded by this here. And then in the second case, when IK star size is greater than this ratio, we just use the fact that we obtain the maximum independent set of the residual graph by removing at most EK prime vertices. So essentially we just need to remove at most one vertex from every edge that was not removed by the matching among the edges having both endpoints in the optimal solution, right? So, and by using this inequality here and the assumption that IK star is lower bounded by this ratio, we immediately obtain the result that we need. Now, this last lemma immediately yields the approximation ratio for our algorithm given by 1 plus k divided by k plus 2. And then the running time of our algorithm is bounded by km square root of n, because we can find the maximum matching by employing the standard algorithm, which runs in order m square root of n time, and then observe that we can use the Hopford-Karp algorithm also to compute the maximum independent set in the residual graph, because we can employ the Koenig-Eger-Vary theorem, and according to this theorem, the cardinality of the maximum matching is equal to the cardinality of the minimum vertex cover. So this establishes our main result. We can actually show that the approximation ratio that we obtained is sharp, because here we have the worst case example. This illustration is for k equal to 3, but we can construct the worst case examples matching the approximation ratio that we obtained for every k, in fact. To conclude, I would like to point out that one dependent set and independent union of cliques are equivalent in bipartite graphs. So when k is equal to 1, we have the 4/3 approximation algorithm for the maximum independent union of cliques problem on bipartite graphs, which is a new result for that problem. Also, for the maximum cardinality matching, there are faster randomized algorithms than the standard method that we use in our analysis. And finally, I would like to point out that the algorithm that we developed works for a more general class of Koenig-Egervary graphs, which include the bipartite graphs. Even though we presented the analysis for bipartite graphs, it directly extends to this larger class of graphs. Thank you for your attention, and here are the references that we cited in this presentation.